Barry from Barry Science Lab, and today we'll be looking at a few different kinds of fluid flows. U of x, y, z, which is commonly abbreviated as u of x, where x is the position vector, can be equal to some parametric function of x, y, and z. Now, the ones we will study today are rotational flows. Flows of the form a, y, comma, b, x, comma, 0. Now, let's study how this looks. Of course, there's no z coordinate, which means we can just study it in the xy plane. So let's first assume a and b are positive. That means that close to the origin, we're not going to see much, but as you get further out, you're going to see more and more stuff occurring. So that's one kind of fluid flow, where it gets more intense radially. But there's another kind of fluid flow, where you can just make these A and B negative. Everything is flipped. Now, if you want it to get more intense inward, you can divide it by x and y, but beware that not only does that cause calamity at x equals 0, but that's something that we'll study for another time. Well, maybe we'll study it today. Who knows? So, when studying how these velocity fields act, there are two big things we have to take into consideration. Vorticity, which is essentially how well the fluid flows. So a vorticity is how much it curls up, it twists itself, and accordingly, it's just the curl of our velocity field. And of course, the distortion matrix tells us how distorted, if we have an initial material volume, omega, which is composed of a bunch of fluid particles, and we throw it into the liquid flow, then this records how distorted its shape is after being in the flow for some time. So this is equal to 1/2 multiplied by, and of course, later we're going to consider velocity fields that change in time. But today we're not doing that. Yes, this is the gradient of a vector. All right. So now let's try it with a very simple problem. Minus ny minus nx, 0. First, we find the vorticity. Now, if you recall the informal definition for nabla, then you'll realize that this cross product is essentially like taking the determinant of the following matrix. Now we plug in ux, uy, and uz. Now uz is just 0, ux is negative ny, and uy is negative nx. So these entries are the only things that are going to change. So we take the determinant of that. What do we get? We get this is 0, then we go the other way, and we get partial z minus nx, which goes to 0. Then for the second component, we get partial z minus ny minus 0. So this also goes to 0. And then, since we're taking the partial derivative with respect to a variable that isn't even there, And then the final part, we have the partial derivative of minus nx with respect to x, which is minus n. And then we what do we do? Wait. Well, we subtract let me think that. Oh crud. I haven't made a rotational field.
But you found your own mistake?
Yeah, it's fine. So now you will realize that if I plug this in, you have minus partial y minus ny, which means that this is just the zero vector. Yeah, that's right. If you have something that only goes radially inward, it's not going to have any curl. It's not curling, it's just going in. So to add some sort of curl, you have to make one of these positive, because now we have something like this instead of something like this. So this is what we're looking for instead of this kind of thing. So once we flip one of the coordinates, what do we get? This just gives us minus n, which just gives us 0, 0, minus 2n, which means there is some vorticity. Now, if you look at the distortion matrix, you'll already realize that it should be 0, because we're just rotating a solid object. And indeed, I'm not going to go through the steps right now, it is 0. I skimmed over that because I want to get to the most interesting case. Something like 2y minus x. Like that. How do we do this? Now, of course, the vorticity is just going to be equal to, once again, everything's going to be the zero vector instead of, except for the z coordinate, which is just going to be partial x minus x, which is minus 1, minus partial y 2y, which is minus 2. Now we can find the distortion matrix. Now let's make a quick sketch to see what we're looking at here. Now if we increase in the x direction, we see the y direction increase. But if we increase in, well, technically decrease. If we increase in the y direction, we see the x direction increase by a lot. Which means that this is going to be kind of shrinking as it goes down. So in other words, the intensity of the flow starts out really huge, but it starts getting lower and lower as it moves down. So let's see if we can find that in our distortion matrix. Now the distortion matrix is just going to be, well, entry ij of the distortion matrix is equal to partial u xi xj. That's the definition of the gradient of a vector. So this is going to be 0. Wait, no. This is the definition for the gradient of a vector. But we have to also put a half and then add the transpose. So now this is only going to be non-zero, of course, when we're doing partial uy, partial x, then partial ux, partial y, which are just entries e12 and e21. When we do those, we get eij is equal to 1/2 multiplied by, this is going to be partial uy partial x, which is going to be -1. Then this is going to be partial ux partial y, which is going to be 2, which makes those two entries 1/2 and everything else 0, which means that our distortion matrix looks like this. 0, 0, 0. Wait a second. This is 1, 1, this is 1, 2, this is 1, 3, which means this is 0, 1/2, 0, 1/2 here, 0, 0, 0, 0, 0. There we go. This is our distortion matrix. So as you can see, there's evidently a pretty large amount of distortion here. Thank you everyone for watching, and we'll see you in the next one.